Alrighty, hello. Excuse me, and welcome to lecture. We're gonna pick up today where we left off on Tuesday. And on Tuesday we were talking about gas laws. We're in chapter 6 now, and we spent the majority of class deriving all of these different expressions for how pressure relates to volume, pressure, and temperature of a gas, right? So, for example, we said that if you took the pressure of a gas and multiplied it by that gas's volume, that it equaled some constant number. Likewise, if you took the pressure of a gas and divided it by the moles of gas in that sample, that equaled a constant number. And likewise, if you took the pressure of a gas and divided it by that gas's temperature, it again would equal a constant number. And we use this to develop a series of equations with initial and final conditions. And we then use those to solve problems. Well, today we're going to take all of these little equations and combine them into one. It turns out if you take the pressure of a gas, multiply by its volume, divide by the number of moles in the sample and the temperature of the sample, that these all together will equal a constant number, C. And just like last week, it doesn't matter what that constant is because we can use initial and final conditions to create an equation that gets around needing to know the actual value for that constant. All right, now this equation right here, this equation has a name. It's called the combined gas law. All right, this is the combined gas law. I definitely recommend that you add this to your equation sheets because it will definitely come in handy. And you can use, you can use this equation to solve the next few examples that we're about to do together, but you can also use this one equation to solve all the examples we did in last class. This is like the skeleton key. This equation will unlock all of those problems, and you'll see how it can, because you may be going, well, wait a minute, we did problems last week that only had pressure and volume, but this equation has moles and temperature. You'll see how to handle those situations with this equation in the examples that we're going to do today. So this one is really kind of the omni equation. It will handle all of those examples for you. All right, so let's start off with an example. All right, so a sample of oxygen gas has a volume of 3.62 liters at 1.02 atmospheres and 25 degrees Celsius. If the moles of O2 remain constant, what volume will this sample occupy? At 1.98 atmospheres and 45 degrees Celsius. All right? So, whenever you're trying to solve a problem, the first thing that you want to do, as we've said all semester, is we want to figure out, we want to identify what we're trying to find. All right? And that is located right here. What volume will the sample occupy? All right, so we are after our volume, our final volume of O2. All right, that's what we're trying to find here. Let's take a look at what we're given. All right, now you'll notice that we have, so we were told actually what our, what our initial volume is. We're told right here that it's 3.62 liters. All right. We're also given our initial pressure. Right here, 1.02 atmospheres. In addition, we're given our initial temperature of 25 degrees Celsius. Right here. Now, because we're told that the sample starts, it's got a volume of 3.62 liters at 1 atmosphere and 25 degrees C. Now, both pressure and temperature end up changing, right? We're told that the pressure changes to 1.98 atmospheres. And the temperature changes to 45 degrees Celsius. All right. So this looks like a job for the combined gas law, right? This looks like a job for P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. There's just one problem here. You'll notice that we have final temperature, final pressure. We want to find our final volume. And we're also given initial volume, initial temperature, and initial pressure. There seems to be something missing from this equation. How are we supposed to solve this if we don't know how many moles are in this sample? And you'll notice that this problem does not explicitly state how many moles are present, but that doesn't mean it doesn't give us useful information. We're told right here that our moles of oxygen remain constant. That means that our initial quantity of moles equals our final quantity of moles. In other words, the number of moles present in this sample are not changing. And because they're not changing, because they're being held constant, they actually cancel out of this equation, which allows us to use this equation to solve for our volume. All right, so that is going to be our next move. We're going to solve this algebraically, and then we'll circle back around and get a value. So we have the equation P1 times V1 over T1, remember because moles canceled, it simplifies to P1 V1 over T1 equals P2 V2 over T2. Now we want to solve for our final volume, so we're going to isolate it on one side of this equation by multiplying both sides by T2 over P2. So pressure, final pressure cancels, final temperature cancels, and we get an equation that says final volume is equal to initial pressure times initial volume times final temperature over initial temperature times final pressure. All right, so we're algebraically set up to solve the situation. There's just one last catch that we have to deal with, and that comes in with our temperatures. So you'll notice we're given initial temperature and final temperature in Celsius, all right, in degrees C. And in order to use the combined gas law or any of the gas laws we've used up to this point in time, our temperatures have to be in Kelvin. All right, so we have to do 2 unit conversions before we can actually plug values in. So we need to convert T1 and T2 to Kelvin, and the conversion factor to go from degrees Celsius to Kelvin is you add 273. When you add that to your temperature in degrees Celsius, it converts degrees Celsius to Kelvin. So busting out my calculator, 273 plus 25 is equal to 298 Kelvin. 273 plus 45 is equal to 318. Okay. So with these two temperature units or temperatures converted to the proper units, we can finally set up or plug in values to find our final volume. So V2 is P1 V1 T2 over T1 P2. All right, so that is our initial pressure is 1.02 atmospheres. Actually, I'm going to write this just a little lower. So I've got enough room to work. So 1.02 atmospheres times our initial volume, which is 3.62 liters, times our final pressure in Kelvin, which is 318, divided by our initial temperature in Kelvin, 298, times our final pressure, which is 1.98 atmospheres. If you look, our pressure units cancel and our temperature units cancel, which is good because we're finding a volume. And now we're ready to crunch our numbers. 1.02 times 3.62 times 318 divided by 298 divided by 1.98. All right. So my calculator is giving me a value for our final volume of 1.99000061. But you'll notice, and actually, we can't look at these numbers actually. So I'm just going to look back at the numbers we used in the calculation. You'll notice actually that all of these have the same number of sig figs, right? Our pressure has 3 sig figs. Our volume has 3 sig figs. Actually, both pressures have 3. And both temperatures have 3 significant digits as well. So our answer needs to be limited to 3 significant figures. So we count off, whoops, 1, 2, 3, 0, rounds down. So our final answer would be 1.99 liters. Oh my goodness! Sorry, Rox. I just saw your comment. I was like, "Oh my gosh, you have a headache. Hope you don't get a fever, because that might be the start of COVID." Which fortunately I'm over. I wouldn't wish that on anyone. That a gas law induced headache, though, that's another cure. Actually, the only cure is to do another gas law problem. So let's go ahead and dive into example number 2. These ones tend to be lengthy, so take a lot of practice. All right, let's do another example. Okay, nitrogen gas is stored in a sealed, metal cylinder. Oh, sorry, not period. In a sealed metal cylinder at 25 degrees Celsius. The pressure gauge pressure is 722 torr. If the cylinder let's see, where's my problem? There it is moved to a 16 degree Celsius freezer, what would the pressure be inside? Or here, there's a better way to say this. What would the pressure of the nitrogen gas be? There we go. All right. Again, whenever you're solving a problem, doesn't matter what type, the first thing you want to ask yourself is what? What are you trying to find? And the answer is pressure. We're trying to find the final pressure of the cylinder after we move it to the freezer. Well, what are we given? We are given the pressure initially, right? Our initial pressure is 722 torr. And we're given the temperature at which it has this pressure, T1, 20, whoops, not 5 degrees C, 25 degrees Celsius. What else are we given? We're given that the cylinder was moved to a 16-degree freezer. So there's our final temperature. And one thing that might jump out at you is we're given both of these temperatures in degrees Celsius. Anytime you're going to do a gas law problem, it's just a good habit to convert these to Kelvin. So let's just go ahead and do that while we're dealing with temperature. So to convert from Celsius to Kelvin, you add 273. So our initial temperature would be 298 Kelvin. Our final temperature will be, let's see, 273 plus 16, 289. Kelvin. All right. So now, again, we're given initial and final conditions here. So this might get you feeling like, okay, this is a combined gas law problem. And you would be correct. The combined gas law is P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. And we have several of these components, right? We have our initial pressure, initial temperature, as well as our final temperature. We're being asked to find our final pressure, but we haven't been given numbers for volume. We haven't been given numbers for moles. So how do we handle this? All right, and actually, the information for volume and for moles are both embedded in the problem. First, you'll notice that this cylinder that's storing the gas is sealed. That means if it's sealed, that we're not gaining more moles of gas, we're not losing moles of gas. The fact that it's sealed tells you that your initial quantity of moles equals your final quantity of moles, so moles cancels out of the equation. The second thing that we're told is that we're dealing with a metal cylinder. This thing is solid, it's metal. Metal's volume does not change. So the fact that we're dealing with a metal cylinder, if we were dealing with a rubber balloon, the volume could totally. And now we can use this simplified version of the combined gas law to solve for our final pressure. We just need to multiply both sides of this equation by final temperature. So algebraically, this equation rearranges, and we see that final pressure is equal to final temperature times initial pressure over initial temperature. All right, so now we can plug in our values. Final pressure is equal to our final temperature, which is 289 Kelvin, times, that's final temperature, times initial pressure, 722 torr, over our initial temperature, which is 298 Kelvin. You can see that our temperature units cancel. Kelvin cancels Kelvin. We're ready to crunch some numbers. So we have 289 times 722 divided by 298. So our final pressure, well, my calculator is telling me that the answer is 700.194,631. If you look at sig figs, every number that we use in this calculation has 3 significant digits. So our answer needs to have 3 significant digits. One's going to round down. But there's a problem. 700 torr only has 1 significant digit. 700 is the correct value after rounding, but it only has 1 significant digit. So for this answer, we actually need to write it in scientific notation as 7.00 times 10 to the second power torr. And this is our final answer. After moving the cylinder from room temperature, 25 degrees, to this 16-degree freezer, the pressure of the nitrogen gas inside will drop from 722 torr to 700, or 7.00 times 10 to the second torr. You can't Totally. You can't do 700 torr because it only has 1 sig fig, and our answer must have 3 based on the numbers that we used. Totally, Ariana, this is definitely a difficult problem type. The gas law stuff is not easy. That's why you want to get as many reps in as you can. It's especially at first, Ariana, this looks intimidating, it looks challenging, but as you do more and more of these problems, it'll feel more and more familiar. Rox, it doesn't actually have anything to do with your answer having 1 sig fig, because if the numbers that we had used in this calculation each only had 1 sig fig, 700 would be correct. It's not that you have to use scientific notation whenever there's 1 significant figure. You have to use scientific notation whenever that is the only way to write your answer with the correct number of sig figs. In this case, because we had used 3 numbers with 3 significant figures each, we had to write an answer that has 3 significant figures, and 700 by itself only has 1. So that's why we had to use scientific notation so that our answer would also have 3 significant digits. All right. Now, we've spent a lot of time, actually all of our time, talking about gases, saying that, oh yeah, we've used a constant to derive these equations. And we've always said, don't worry about the constant. It's not important. We don't need to know what it is. Like, don't mind the man behind the curtain, right? But I want to dial us back to the beginning of this lecture, where we said pressure times volume divided by moles times temperature, again, all of a gas, equal to, we've said some constant number C this entire time, but we haven't ever said what that constant is. Well, it's time for the constant to have its moment in the sun. So what is this constant? I'm so glad you asked. This constant is R. R You're like, that's just another letter for the constant. R is known as the ideal gas constant. And it has a value of 0.08206, and it has units of liters times atmospheres divided by moles over Kelvin. If you're wondering why does this unit have such weird, why does this constant have such weird units? Well, you'll notice that liters are a volume unit, atmospheres are a pressure unit, moles are, well, a unit for moles, and Kelvin is a unit for temperature. So that's where the kind of bizarre units for the ideal gas constant come from. Now, here's why the ideal gas constant is cool. If you take the combined gas law, pressure times volume over moles times temperature, equals R, the ideal gas constant, we can rearrange this equation. We can get rid of the denominator, right? Nobody likes a denominator, by multiplying both sides of this equation by moles times temperature. And this gives us an expression. PV is equal to nRT. This equation has a name, and this equation is another one that you want to add to your equation sheet. This is called the ideal gas law, and this thing totally rocks. All right, the ideal gas law is super cool, far more cool than the combined gas law. Here's why. One of the advantages that it has is you don't have to know the initial and final conditions for your pressure, your volume, your moles, your temperature. It just allows you to take one set of data, not initial and final, and solve problems. So that's one reason why it's cool. But honestly, the biggest reason why it's cool is right here. If you know the pressure of a gas, the volume of the gas, and the temperature of the gas, the ideal gas constant allows you to solve for n. Because, right, we always know R's value doesn't change. It allows you to solve for n. Why is that cool? This is cool because n is moles, right? And if you can find moles of a gas, then you can do stoichiometry. Right? We can now use all of these gas quantities, pressure, volume, temperature, to find moles, and then with moles, we can do stoichiometry. We can do percent yields. We can do limiting reactants problems. All those things that we learned previously, now we can apply to all the knowledge that we have of gases and their quantities we can connect those with all that stuff we learned about stoichiometry, percent yields, theoretical yields, limiting reactants, all that stuff. We can connect our knowledge of the gas phase to that information. All right, so this ideal gas law kind of bridges the gap between the two and allows us to do problems like the following. All right. So consider the following problem. Calcium carbonate which is a solid, decomposes at 453 degrees Celsius and 1.02 atmospheres of pressure into solid calcium oxide and carbon dioxide gas. All right. Now, what volume of carbon dioxide will be produced if 1.00 grams of calcium carbonate completely decomposes. All right. Actually, sorry, hang on. That is the ultimate question that I'm going to ask, but I'm actually going to give it to you in a couple steps. Here, part A. Write a balanced chemical equation for this reaction. Part B is what volume of carbon dioxide is produced if 1.00 grams of calcium carbonate decomposes. Okay, there we go. So first, let's not be overwhelmed by part 2 of this problem. Let's take the first part, which I know we can all do. All right. Part A is write a balanced chemical equation. So you'll notice this is actually this problem is excellent because it tests gas laws, it tests stoichiometry, and it tests nomenclature, right? we have to remember how to name things if we're going to write a balanced chemical equation. So first, we're dealing with calcium carbonate, which is an ionic compound. When you look at the periodic table, calcium is a main group element. It'll have a charge of +2. Carbonate is a polyatomic ion. It's one of those ones that you just need to know. Hopefully it's on your equation sheet if you don't have it memorized. And it is CO3 with a charge of -2. So because our charges are the same here, calcium and carbonate are going to combine in a 1-to-1 ratio. So this will be CaCO3, and it is in the solid phase. All right, we're told that it decomposes into solid calcium oxide. All right, that's our next name that we need to decipher, right? Calcium oxide. We already know the charge of calcium. It's +2. Oxide, when you look at the periodic table, oxygen wants to gain 2 electrons to be like its nearest noble gas, neon. So it will pick up a charge of -2, again, combining with calcium in a 1-to-1 ratio. So this is solid calcium oxide, plus our final, oh, did I mess this up? I sure did. Hang on one second. Gotta copy and paste into the right layer. There we go. All right, the third and final product here is carbon dioxide. That is a covalent compound, so we don't need to worry about charges. We just follow the laundry list. There's 1 carbon, whoa, I don't want this in pink. 1 carbon and 2 oxygen atoms in carbon dioxide. So we've written our reactants, we've written our products. Now we need to balance this chemical equation. So we have calcium, carbon, and oxygen. Calcium, carbon, and oxygen. We have 1 calcium, 1 carbon, 3 oxygen on our reactant side. On the product side, we have 1 calcium, 1 carbon, and 1 plus 2 oxygen atoms. So this equation actually is balanced as is. And before you go and cry foul, I know whenever something like this would work out in lecture, I would always say, like, that's just the professor picking the easiest examples for himself. The ones on the test aren't going to be that easy. I'm here to tell you that I actually put this equation, this actual equation, on exams. This is one that I've used in the past. I use ones like it because I'm also testing your confidence level. On the test, if you have to balance an equation and it's already balanced, check. If it's already balanced, then don't mess with it. It's a gift. It's a free gift from me. So I put a range of problems on the test. Some are easier, some are harder. But just because something seems easy or too easy, don't overthink it. Have the confidence to roll with the correct answer. All right, so this is the balanced chemical equation for part A. Now let's take a look at part B. What volume of carbon dioxide is produced if 1 gram of calcium carbonate decomposes? All right, Well, I'm going to blank out our balanced chemical equation for a minute. We'll come back to it. But first, let's talk part B. Let's talk about what we are trying to find first and foremost. All right, so first and foremost, what are we trying to find here? We're trying to find the volume of CO2. All right, we're trying to find the volume of CO2. Let's take a look at what we're given. All right, let's take a look at what we're given. So we are given, well, you'll notice that we're actually given a temperature. We're told that this reaction takes place at 453 degrees Celsius. And we're given a pressure, right? So we're given the temperature, not T2. We're given the temperature of CO2, carbon dioxide, 453 degrees Celsius. And we're given the pressure, because this gas is forming under 1.02 atmospheres of pressure. Let's see, what else are we given? We are given the grams. We're also told that we have 1.00 grams of calcium carbonate. Now, we're given volume, or sorry, we're being asked to find volume. We're given temperature and pressure. So you might be thinking gas law. You'd be right. When you look at the ideal gas law, it says the pressure of our gas, CO2, times its volume is equal to moles of CO2 times the ideal gas constant times the temperature of CO2. Now we've been given our temperature, we've been given our pressure. You always know the ideal gas constant, right? Because it's always equal to 0.08206. So have that on your equation sheet. You always know R. We're being asked to find volume. The only thing, we need one piece to find volume algebraically. And that is, we need moles of CO2, right? We need to find our moles of carbon dioxide. Now, what's the one piece of given information we haven't used yet? Grams. Unfortunately, it's not grams of calcium, or sorry, it's not grams of carbon dioxide, it's grams of calcium carbonate, and we need moles of carbon dioxide. This is where part A comes into play. Because we just wrote a balanced chemical equation in which that gives us the mole-to-mole ratio to convert from moles of calcium carbonate to moles of carbon dioxide. So if we knew moles of calcium carbonate, we could find moles of CO2. Turns out that we can use the chemical formula of calcium carbonate to calculate its molecular weight to convert our gram of calcium carbonate into moles. So we need to use stoichiometry to do that last part to get our moles of CO2. Then we use the ideal gas law to find the volume of CO2. All right, so there's going to be kind of a two-step deal to get to our answer. And it's going to start with using our balanced chemical equation. So I'm going to move this up. And we're going to begin this process by converting our mass of calcium carbonate to moles. All right, so our first step is we need to calculate our mass. Now, calcium has an atomic mass of 40.08. Carbon has a mass of 12.01. And oxygen has a mass of 16.00, but we have 3 of them present, so we need to multiply this by 3. All right, so 16 times 3 is 48, plus 12.01, plus 40.08. These add up to 100.09, excuse me. And you'll notice that for these values, they all have their last significant digits in the first decimal place. Our answer has its last significant digit in the first decimal place as well. So there's no need to round or anything. Now, we want grams. Oops. Grams of calcium carbonate to cancel. We want to convert this to moles of calcium carbonate. So our mass will go in the denominator, 100.09. And grams of calcium carbonate will cancel. Now, next, we want to find moles of CO2. So we want to convert from moles of calcium carbonate to moles of carbon dioxide. And this balanced chemical equation tells us that there is a 1-to-1 mole ratio between moles of calcium carbonate that decompose and moles of carbon dioxide that form. So we're ready to crunch numbers. 1.00 divided by 100.09 comes out to be 0.009999101 is what my calculator is telling me. Our molecular mass has 5 sig figs, but our initial mass only has 3, so we have to round to 1, 2, 3. This one rounds down. So we have 0.00999 moles of carbon dioxide. All right, now we've done a lot of work, and it's really easy when you're doing these problems to think, okay, sweet, that's my answer. But you have to remember what you're trying to find in the first place. We are after volume. the volume of CO2. Remember, we weren't asked to find moles of CO2. We want the volume of CO2. And we need the moles of CO2 so that now we can solve this equation, right? The ideal gas law. Now we know the pressure, the moles, the ideal gas constant, and the temperature. So we have some algebra to do to solve for our volume. All right, I'm going to get rid of my chemical equation because we don't need it at this point. So we have PV equals nRT. Divide both sides by pressure so that it cancels and we isolate volume. We get volume is equal to our moles times R times T over P. So if we punch in our numbers here, our moles are 0.009. You know what? I'm actually gonna run out of space up here. I don't know what I was thinking. Shift this down. All right, so sorry, our moles are 0.00999 moles times the ideal gas constant, which is 0.08206 liter atmospheres per mole Kelvin. We were told that our temperature was 453 degrees Celsius divided by our pressure, which was 1.02 atmospheres. All right. Now, one of the things that you may have noticed as I work problems is that I always include the units when I'm doing them. And this is why. Because if you've done everything right, by the time you get down to crunch your numbers, we're solving for volume. All of our units should cancel except for our volume unit. So you'll notice, for example, that we have moles in our denominator, moles in our numerator, they cancel. We have atmospheres in a denominator, atmospheres in a numerator, they cancel. But take a look at our temperature units. I have Kelvin in the denominator and degrees Celsius in the numerator. These do not cancel. If I didn't include my units when I was working this problem, I wouldn't see that. I would punch this into my calculator, my answer would come out wrong. But because I've included my units, they're there to catch me if I make a mistake, if I forget to do a unit conversion. So we need to convert .453 degrees Celsius to Kelvin by adding 273. So this will come out to be 453 plus 273 is 726 Kelvin. Oops. So this is 726 K, and now my temperature units cancel. So, Rox, this deal right here, this is the ideal gas constant R, who has units of our units are liters times atmospheres divided by moles and Kelvin. So those are just the units for the ideal gas constant R. Alrighty. All of our other units canceled. The only unit left uncanceled is liter, which is good because we're solving for a volume. So now we're ready to crunch our numbers and get our final answer. 0.00999 times 0.08206 times 726 divided by 1.02. So volume is 0.58349,004. Sig figs wise, we're limited to 3 by a few, by our quantity of moles, our pressure, also our temperature. So you count off your first 3, 4 rounds down. So the volume of CO2 is equal to 0.583 liters. Alrighty, so that is the final answer for this problem. It was a long one, but this is like the full metal version. This has nomenclature, it has balancing equations, it has stoichiometry and ideal gas law, all rolled up into one. All right, I've got another one very similar to it, locked and loaded and ready to go. All right, so let's take a look at the following example. Aqueous hydrochloric acid reacts with solid sodium hydride at 25 degrees Celsius, and let's see, I can't quite see the pressure I wrote in my notes. Okay, and 0.97 atmospheres. To produce hydrogen gas and aqueous. Actually, hang on, I have to fix this problem real quick. I'm just going to change the phase to gaseous hydrochloric acid. Will react with solid sodium hydride at 25 degrees Celsius and 0.97 atmospheres to produce H2 gas and solid sodium chloride. All right, part A. is write a balanced chemical equation. Part B is O is if, or actually, rephrase one more time. Determine the mass of sodium hydride that reacted if 4.80 liters of H2 was produced. All right. This problem's another twist, another something different, but it starts with a very familiar beginning, which is write a balanced chemical equation for this reaction. So we're going to take this thing one step at a time. I'm just looking at the clock right now. We may not have time to finish this problem. We'll definitely get through part A, but if we don't have time for part B, we'll pick it up in lecture on Thursday. All right, so let's write a balanced chemical equation. So first, we have to reach our mind back and recall our acid nomenclature. Right, so we're dealing with a hydroic acid. All right, that means that our acid, the ion that our acid was based off of, ends in an IDE. Whenever you're dealing with an ic acid, that acid is based off of the ide anion. So this is based off of chloride, which is just chlorine as an ion, right? So it's Cl with a charge of -1. That means hydrochloric acid will be HCl, right? You give it 1 proton for every negative charge on your ion. We're told that it reacts with sodium hydride. Now we know that sodium is an ion. Its charge, we figured out from the periodic table. Sodium has 11 electrons. Its nearest noble gas is 10, so it loses 1. Now hydride, when hydrogen is an ion, that means it has gained an electron to become like neon. So this is H minus. So sodium and hydrogen combine in a 1-to-1 ratio to make solid sodium hydride. All right, now, the products of this reaction are, we've been told, H2 gas and solid sodium chloride. Now, sodium has a charge of +1, chloride has a charge of -1, so these combine in a 1-to-1 ratio to make solid sodium chloride. So this is not our balanced chemical equation, possibly, but it is, we do have our reactants and our products written out, and now we're ready to balance this equation. All right, so let's look at the, oh my gosh, did I do it again? Let's see, HCl, oh my goodness, wait, hang on, I think this is actually already balanced. Well, I guess lightning can strike twice because we have 2 hydrogens, 1 chlorine, and 1 sodium on the reactant side. I don't know why I put the subscript here. We have 2 hydrogen, 1 chlorine, 1 sodium. So turns out balance. All right. Now, we do not yet, I don't feel like we have enough time to complete this problem, and I don't want to rush it, and I don't want to break off in kind of a weird place. But let's go ahead and set up the thought process, all right, of how you're going to approach solving this problem. So remember, we've been asked to find the grams, the mass of sodium hydride that reacted. All right. And we've been told, we've been given a pressure. Well, first, actually, we've been given a volume of hydrogen, 4.80 liters. We've also been given a pressure, right, 0.97 atmospheres, and we've been given a temperature, 25 degrees Celsius. These three, in addition to the ideal gas constant, will allow you to find moles of hydrogen. So use this information to find moles of hydrogen, and then use the balanced chemical equation to convert from moles of hydrogen to moles of sodium hydride. That's the path forward. The first equation, are you talking about... Oh, okay. Sorry, Rox. I just now got your question. Okay, so here's how. So when you're balancing this situation, yeah. Exactly it. All right. Okay, so go ahead and give this a crack. Over Wednesday. Yep, the other one is from sodium hydride. Totally. See what you come up with. I'll do this problem at the beginning of class next lecture, and we will and you can see if you got your answer right. So that's all for today. I will catch the rest of you in lab.